Good morning, learners and viewers. Welcome to the session of Masters of Business Administration. Today we will be continuing with our subject Operations Research, that is MMP 001. In our previous session, we were talking about linear programming, problem formulation. To continue with that, I'm just briefing how this graphical equations are solved. Suppose we take up equation y is greater than minus 3x plus 1. So we have to plot, since this is a linear equation, in linear equation, so we will have our graph as a straight line. Now the thing is that how to plot this on a graph. So normally what we do, we try to convert, or we should convert this equation into an intercept form equation. And normally what we use, what intercept form is, that is x by a plus y by b equal to 1. Taking up that equation, we will be removing that sign, inequality sign, and we will be equating it. So that means that equation y greater than minus 3x plus 1 will become now y equal to minus 3x plus 1. So we will be taking this 3x on the left side and converting it into a equation of the form 3x plus y equal to 1. Now we have to convert this equation into a form of x by a plus y by b equal to 1. What we will be doing, we will be bringing down this coefficient of x3 on the denominator. That will be 1 by 3 plus y upon 1 equal to 1. That means 1 by 3 comma 0 will be the point on x-axis where this line will cut. We can see that it is almost 0.33 over there. And similarly for y-intercept, it will be 0 comma y. You can see that that is at green point on the y-axis. Now, what we have to keep in mind, since this equation does not have any equal to sign with greater than sign, that means its graph will be a dashed line. You can see a violet line, that is basically the graphical representation of this inequation. Now, to test the feasible region for this equation, so normally what we do, we put up the value 0 comma 0, that is the origin value in the equation. That means we will be replacing y with 0 and x with 0. We get 0 is less than 1, but that is wrong. That means in that case, the region on the other side of 0 comma 0 will be your region for the solution. We have to keep that thing in mind. If it would have been 0 less than 1, so in that case, its area will be towards the origin. Now, if two inequations are taken simultaneously, one is y is less than 2x plus 5, and the other one is y greater than minus x. We can remember that y equal to x or y equal to minus x is a line which is equally inclined on the axis. Since here in this case, our problem, it is y greater than minus x. That means it will be a line which will be inclined towards the left side. The blue line is the line for the inequation y greater than minus x. Similarly, for this y less than 2x plus 1, this red line is the equation, is the graph for the equation. Now we have to check the area which is common to both these lines. In that case, we will be using the same method. We will be replacing x by 0 and y by 0. So here in this case, it will be 0 less than 5. That is correct. That means its region will be towards the origin. And y is greater than equal to minus 2 will be a line, and its area will be towards away from the on the rather we can say on the first quadrant. So the purple area is the area which is common to both the lines. In that case, any point which is on the purple side can be treated as or is the solution, common solution for both the equations. Now, we'll start with linear programming problems. The problem in a statement form will be given. So in that case, we should be aware with basic terminologies which are used. The word linear is used to describe the relationship among two or more variables which are directly or precisely proportional. What is meant by programming? Programming means the decisions which are taken systematically by adopting alternate courses of action. While we will be transforming the statement into the equation or in equation form, so we should be aware of different terminologies. So first we'll start with decision variables and their relationship. The decision variables refers to any candidate. It can be a person, service, projects, job, tasks, competing with other decision variables for limited resources. These variables are usually interrelated in terms of utilization of the resources and need simultaneous solution. That is, the relationship among these variables should be a linear. Second one is objective function. The linear programming problem must have a well-defined objective function to optimize the result. For instance, minimization of cost or maximization of profits. It should be expressed as linear function of decision variable, which is normally in the form of z equal to x1 plus x2, where z represents the objective, that is minimization of maximization, and x1 and x2 are the decision variables directly affecting the z value. Constraints. There would be limitation or resources which are to be allocated among various competing activities. These must be capable of being expressed as linear inequalities or inequalities in terms of decision variables. Fourth one is alternative courses of action. There must be presence of alternate solutions for the purpose of choosing the best or optimum one. Fifth one is non-negativity restriction. All variables must assume non-negative values. If any of the variable is unrestricted in sign, a tool can be employed which will enforce the negativity without changing the original information of a problem. Linearity and divisibility. All relationships, objective function and constraints must exhibit linearity. That is, relationship among decision variables must be directly proportional. It is assumed that decision variables are continuous. That is, fractional value of variables must be permissible in obtaining the optimal solution. Seventh one is deterministic. In linear programming, it is assumed that all model coefficients are completely known. For example, profit per unit. Now, what are the advantages and limitations of linear programming? If we talk about the advantages, it helps in proper and optimum utilization of the scarce resources. It helps in improving the quality of the decision. With the use of this technique, the decision maker becomes more objective and less subjective. It even helps in considering other constraints operating outside the law. Many a times, it hints the manager about the hurdles faced during the production activities. And if we talk about the limitations, The treatment of variables having non-linear relationship is the greatest limitation of this LPP. It can come out with non-negative, non-integer solutions too, which would be many a times meaningless. It rules out effect of time and uncertainty conditions. Generally, the objective set will be a single, and on the contrary, in the real life, there might be several objectives. Large scale problems tends to be unaccommodative to solve LP. Now, what are the formutation of LP, linear programming models? Linear programming family includes formulation of linear programming problems, what we call it as LPP, linear programming graphical solutions, linear programming simplex solutions, linear programming assignment problems, and the fifth one is transportation problems. Now, what are the steps for formulating LPP? First of all, we have to identify the nature of the problem, whether it is a problem related to maximization or minimization. Secondly, we have to identify the number of variables to establish the objective function. Third one is to formulate the constraints. Fourth one, develop non-negativity constraints. Now we take up a problem and we have to solve it graphically. The problem is a rubber company is engaged in producing three different kinds of tires A, B, and C. These three different tires are produced at companies' two different plants with different production capacities. In a normal 8-hour working day, plant 1 produces 50, 100, and 100 tires of A, B, and C respectively. And similarly, plant 2 makes 60, 60, and 200 tires of type A, B, and C respectively. And the monthly demand of tire A, B, and C is 2,500, 3,000, and 7,000 units respectively. And the daily cost of operation of plant 1 and 2 is rupees 2,500 and rupees 3,500 respectively. Find the minimum number of days of operation per month at two different plants to minimize the total cost while meeting the demand. Now, here we can see that we are talking about three types of tire, and we have two plants. And what will be produced? Tires will be produced. And where will they be produced? They will be produced at two plants. So we assume that how our assumption will start. We assume that daily production or daily cost of operation in plant 1 be X1 and the daily cost of operation in plant 2 be X2. In the last line, we just find the minimum number of days. That means this is a problem which is related to minimization. As we have already discussed, it is represented by capital Z equal to. Now, the problem is related to daily cost. That means daily cost into number of your daily cost of operation for the plant. That means we will be converting this. We will be multiplying 2,500 with X1 and 3,500 with X2, and we will be adding it. That means we have to minimize Z equal to 2,500 X1 plus 3,500 X2, which is subjected to constraints. Now, what are the constraints? Under what conditions? Constraint means what are the conditions under which this has to be achieved. Now, go back to the problem where we can see that tire A has the capacity of 50, tire B 100, and tire 3 is again 100. And in plant 2, it is 60 for type A, 60 for type B, and 200 for type B. So coming down, how the demand constraints are formulated. 50x1 plus 60x2. Secondly, I'm not talking about the capacity of the What was the demand of the monthly demand of the tires? I'm just talking about the left side of the equation. It is 50x1 plus 60x2. Second one will be 100 plus 60. 100x1 plus 60x2. And the third one will be 100x1 plus 200x2. Now, how our one information is again left right now to be transformed. That is the capacity or the demand of tire A, B, and C, which is 2,500, 3,000, and 7,000. How to place it in the inequations. Type A is 2,500, so that means in the first equation, that is 50x1 plus 60x2. On the right side, it will be 2,500. I'm not discussing anything about the sign. Secondly, it is 3,000. So that means our second equation will be 100x1 plus 60x2, and on the right side, it will be 3,000. And for the third one, it will be 100x1 plus 200x2, and on the right side, it will be 7,000. These are the demand constraints. And right now, the equations are without sign. How to place that sign? We have to go back to the problem. We can see over there the monthly demand is of tire A is 2,500. So that means left hand side has to be greater than 2,005 on the right side. That means going back to equation 1, it will be 50x1 plus 60x2 greater than equal to 2,500. Similarly, for second case, it will be 100x1 plus 60x2 greater than 3,000. And for the third equation, it will be 100x1 plus 200x2 greater than equal to 7,000. These are the demand constraints. And now, we are very well aware of that production, cost, are never negative. So that means x1 and x2 both will be greater than equal to 0. And they are the non-negativity constraints. Now, going back how to solve it graphically. We have the equations right now on the screen, the right side. These are the equations 50x1 plus 60x2 greater than equal to 2,500. What we will be doing? We will be converting these equations into intercept form. That means it will be x1 upon 50. So the line will be touching x coordinate at 50, 0. Here we can see that a line is plotted over there, and all the lines, the intercept will be transformed over there. That means we will be having 6 intercepts or 6 points directly on the on the axis line. We have to check the region now. We have to put 0, 0. That means we will be replacing x1 by 0 and x2 by 0. In first case, it will be 0 greater than equal to 2,500. So what we will be doing? We will be, and we have to minimize it. So all the 3 areas will be towards 0. In that case, we have to find out the common region on all the 3 lines. So we can see this shaded region as the common region. So we can see over there are 4 points A, B, C, and D. We have to take these coordinates of A, coordinates of B, coordinates of C, and coordinates of D. We will be placing this. Coordinate A has 70, 0. Coordinate B has 20, 25. Coordinate C is 30, 33.33. And coordinate D is 0, 50. We will be substituting these values in the minimization equation, which is z equal to 2,500 x1 plus 3,000 x2. So we are going to get 4 values. We can see that we have to minimize, so that means it comes out to be 1,24,990 for C, that is 10,33.3. That is our conclusion. Now, converting going one step further. Here, the problem is somewhat like that, but we have different constraints in it. We will be talking about supply and production and machine hours. This will be treated as the constraints. A firm that makes product X and Y has a total production capacity of 9 tons per day, X and Y requiring the same production capacity. The firm has a permanent contract to supply at least 2 tons of X and 3 tons of Y per day to another company. Each one of X requires 20 machine hours production time, and Y requires 50 machine hours production time. The daily maximum possible number of machine hours available is 360. All the firm's output can be sold, and the profit set is rupees 80 per ton for X and rupees 120 per ton for Y. You are required to determine the production schedule to maximize the firm's profit. So what we will be doing, we will be taking two constraints because we are talking about X and Y as the two plants. So here, X1 be the number of tons of product X and X2 be the number of tons of product Y. What is the objective function? We have to maximize the total profit. And the total profit maximization will be done when the firm has a cost of 80 per ton for X and 120 per ton for Y. So that means Z will be equal to 80x1 plus 120x2. This is subject to the different constraints. Going back to the problem, we have machine R constraint, that is 20x1 plus 50x2 should be less than equal to 360. X1 should be greater than equal to, because the firm has a permanent contract of supply of at least 2 tons of X and 3 tons of Y per day to another company. That means X1 should be greater than equal to 2 and X2 should be greater than equal to 3. These are the supply constraints. Now what the production time? What are the production capacity? That means that is X1 plus X2 should be greater than equal to 9. That is the production constraint, and it is on the very first line. Has a total production capacity of 9 tons per day. Similarly, production cannot be negative. We are talking about the production. The production in both X1 and X2 cannot be negative. So that means X1 and X2 both are greater than equal to 0. These are the non-negativity constraints. Now, again, the same method has to be followed. We will be converting the equation into intercept form, and we will be finding out the different intercepts. If we talk about 20x1 plus 50x2 equal to 360, so we will be dividing both sides by 360. It will be 20x1 by 360 plus 50x2 by 360 equal to 1. And we will be converting in x1 by a. That means it will be 360 divided by 20, which comes out to be 18. And 360 divided by 50, which is 7.2. X1 by 9 plus x2 by 9 equal to 1. So in that case, x1 will be 9 and y will be 9. And x1 by 2 equal to 1. So that means x1 will be 0, x1 will be 2 and y will be 0. Similarly, x2 will be 3, x1 will be 0 and x2 will be 3. Now, plotting up these equations on the graph, we can find out this common region as, which is the feasible region is A, B, C and D. So we will be finding out their coordinates by simply solving them simultaneously. How to solve two linear equations simultaneously? The best feasible method is by elimination method. So we have these values A, B, and C. We have found out because on graph paper it can be plotted, and in that case there is no need of calculating it. A, B, C, D. We have to write them their coordinates. That means x1, 2, x2, 3. B will be 6, comma 3. C will be 3, comma 6. And D will be 2, comma 6 by 6.4. So we will be placed by putting all these values together in the main objective function. That is maximize z equal to 80x1 plus 120x2. Putting up all the values, we get four values, that is 520, 840, 960, and 928. So we have to see which value has the maximum value. Here we can see that 960 is the maximum value. That means if company produces 3 units, 3 tons of product X and 6 tons of product Y, the profit will be maximized. Now we move to the very interesting part of operations research, that is transportation problem. That is the second method, rather third method. Transportation problem is associated with day-to-day activities in our real life and many deals with logistics. It helps in solving problems on distribution and transportation of resources from one place to another. The goods are transported from a source or sources, that is, for example, we can say factories, to set of destinations, that is, warehouses, to meet the specific requirement in the open market. Or we can say that transportation problems deals with the transportation of a product manufactured at different plants, that is supply origins, to a number of different warehouses, that is treated as demand destinations. The objective is to satisfy the demand at destinations from the supply constraint at the minimum transportation cost possible. For achieving this objective, we must know the quantity of available supplies and the quantities demanded. We must also know the location to find the cost of transportation, 1 unit of commodity from the place of origin to the destination. This will be helpful for making strategic decisions involving the selecting optimum transportation routes so as to allocate the production of various plants to several warehouses or distribution centers. This will be helpful in minimizing the various costs such as total transportation cost, distribution cost or shipping cost, and the production costs. How modeling of transportation problem is done. Transportation problem can be expressed in two ways. First one is mathematical representation, and the second one is network representation. If we talk about mathematical representation, the transportation problem applies to situations where a single commodity is to be transported from various sources of supply, that is origins, to various demands, that is destinations. Let there be m sources of supply, S1, S2, S3 till Sn, having A1 units of supplies respectively to be transported among n destinations, that means D1, D2 till Dn, with Bj units of requirement respectively. Let Cij be the cost for shipping 1 unit of the commodity from the source to destination for each route. If Xij represents the units shipped per unit from the source to destination, then the problem is to determine the transportation schedule which minimizes the total transportation cost of satisfying supply and demand conditions. Now, maximization transportation problem. In this type of problem, The objective is to maximize the total profit or return. In this case, convert the maximization problem into minimization by subtracting all the unit cost from the highest unit cost given in the table and solve. We will see how this is done. This is what I said just right now, what this transportation model, network representation of transportation model is all about. We can see there are different vendors. Different vendors are providing their parts to plant where they are assembled or manufactured or transformed. They are again sent to the destination distribution centers, and from the distribution centers, it is again routed to retailers. So this is the transportation model, which is represented by a network diagram. Now, general representation of transportation model. The transportation problem can also be represented in a tabular form, as shown in the table. Let Cij be the cost of transporting a unit of product from ith origin to jth. Ai be the quantity of commodity available at source I. Bj be the quantity of commodity needed at destination j. And Xij be the quantity transported from ith source to jth destination. So this is convert how this is drawn. Different columns and rows, the information which is provided in the problem is converted into a matrix form, rather we can say that a tabular form, which consists of rows and columns. S is for supply and D is for demand. When we have to see, first of all, the first condition, what we have to keep in mind, that demand should be equal to supply. What we will be doing, we will be submitting all the values of column 1, that is D1, and it will be B1. D2, it will be B2. When we will be adding all these along with the supply, that is A1, A2 till AM. Numerically, these values are equal. If the total supply is equal to total demand, then the given transportation problem is a balanced one. Now, under what is unbalanced transportation problem? When the total supply of all the sources is not equal to the total demand of all destinations. The problem is an unbalanced transportation problem. In that case, total supply is not equal to total demand. Case is there when demand is less than supply. In real life, supply and demand requirements are rarely equal. This is because of variation in production from the supplier end and the variation in forecast from the customer end. Supply variations can be of various reasons, such as shortage of raw material, labor problem, improper planning, and scheduling. Demand variations may be because of changes in customer preference, change in prices, and introduction of new products by competitors. These unbalanced problems can be easily solved by introducing a dummy source or and dummy destination. So we have to see how this can be or how this is implemented. If the total supply is greater than total demand, a dummy destination, यानी कि dummy column with demand equal to the supply surplus is added. If the total demand is greater than the total supply, a dummy source, dummy row, with the supply equal to demand surplus is added. The unit transportation cost for the dummy column and dummy row are assigned zero values because no shipment is actually made in the case of dummy source and dummy destination. But these are the constraints what we have to keep in mind while solving the problem. Now, how to get the initial feasible solution? First step one is formulate the problem. Formulate the given problem and set up in a matrix form. That means in the form of row and columns. Check whether the problem is balanced or unbalanced transportation problem. If unbalanced, add dummy source row or dummy column destination column as required. Second step is obtain the feasible initial feasible solution. For obtaining this, we have three methods. First one is northwest corner method, that is NWC. Row and column minimum method, that is RCMM. And the third one is Waddell's approximation method, that is WEB. The transportation cost of the initial basic feasible solution through Waddell approximation method when will be the least when compared to the other two methods, which gives the value nearer to the optimum solution or optimum solution itself. Basic feasible solutions. The problem with m sources and n destination has m by n variables and m plus n constraints. The constraints are not independent, but each m plus n minus 1 of them are. This implies the fundamental property. Every basic contains exactly m plus n minus 1 variables, and each constraint contains at least one basic variable. We mark all cells that correspond to the basic variables. How they are done. The table will contain m plus n minus 1 marked cells. Number two, every unmarked cell has a value 0. Number three, each row contains at least one marked cell. Next one is each column contains at least one marked cell, and consequently there always exists a row or column with exactly one marked cell. So, the first method, what we said, was northwest corner method. It is the easiest and the simplest method to adopt. Select the northwest, that is the upper left corner, cell of the table and allocate the maximum possible units between the supply and the demand requirements. During allocation, the transportation cost is completely discarded, not taken into the consideration. Delete that row or column which has no values, that is fully exhausted for supply or demand. Third one, now with the reduced table, again select the northwest cell and allocate the available values. Repeat step 2 and 3 until all the supply and demand values are 0. Obtain the initial basic feasible solution. Second case is Waddell's approximation method, that is where what is done, what is the procedure of solving problem with one method. Calculate penalties for each row and column by taking the difference between the smallest cost and the next highest cost available in that row or column. If there are two smallest costs, then the penalty is 0. Second one, select the row or column which have the largest penalty and make allocation. In the cell having the least cost in the selected row or column, if two or more equal penalties exist, select one where a row or column contains minimum unit cost. If there is again a tie, select one where maximum allocations can be made. Delete that the row and column which has satisfied the demand and supply constraints. Repeat step 1 and 2 until the entire supply and demands are satisfied. And the fifth step is obtain the initial basic feasible solution. The third method was row and column minimum method, or LCM method. Select the smallest transportation cost cell available in the entire table and allocate the supply and demand. Delete that row and column which has exhausted. The deleted row and column must not be considered for further allocation. Again, select the smallest cost cell in the existing table and allocate. Note, in case if there are more than one smallest cost, select the cell with maximum allocations can be made and obtain the initial basic feasible solution. The initial solution obtained by any of the three methods must satisfy the following conditions. The solution must be feasible, that is, the demand and supply constraints must be satisfied, which is also known as ring conditions. The number of positive allocation n must be equal to m plus n minus 1, where n is the number of rows and n is the number of columns. Degeneration. When the number of fields held is less than the number of rows plus the number of column minus 1. Now we take up a problem. How to solve a transportation problem with northwest corner method. The left side, what we can see is the problem which is given to us. We have to find out a feasible solution for this equation in which transportation problem can be solved. So here we can see that available condition is 250, 300, 400, which comes out to be, when we are going to add up, it comes out to be 950. And the requirement is again 200, 225, 275, 250, that is 950. That means we can see that demand is equal to supply, or what is required is equal to what is available. Now, as we said in northwest corner method rule, we have to take the left corner, which is here in the first cell, which has an allocation of 11 units. We take out the maximum possible units between 250 and the demand requirement 200. We place a 200 over there, delete that row and column which has no values, which is fully exhausted for the supply or demand. Now with the new reduced table, again select the net worth corner rule and allocate the available values. So what we will be doing, this will be 200 has exhausted, we are left with 50, so we will be allocating 50 for EA. From 225, 50 is reduced, so we will be placing 175 over there. And we will be subtracting 175 from 300, we get 125. We will be subtracting 270, we will be subtracting 125 from 275, so we will get 150. And lastly, we are left with 250. That means what we have done, what we have calculated, what we have assumed is absolutely correct. Now we have to calculate the transportation cost. So what we will be doing, we will be multiplying these two values in the cells. So that means it will be 200 into 11 plus 50 into 13 plus 18 into 175 plus 14 into 125 plus 13 into 150 and 10 into 250, which comes out to be 12,200. So by NWC method, we got the cost as 12,200. Now we move to web method. Problem is same. We are solving that problem with web method. Initially, what we are supposed to do, calculate penalties for each row and column by taking the difference between the smallest cost and next highest cost available in that row or column. If there are two smallest costs, then the penalty is 0. Here, what is happening? The largest difference is 5 in the first column. 16 minus 11 is 5. 21 minus 16 is 5. As the minimum cost is in C11, 11, we will allocate minimum of 200 and 250 here. Minimum is 200, we have allocated. Moving further, select the row and column which has the largest penalty and make allocations. In the cell having the least cost in the selected row or column, if two or more columns, more equal penalties exist, select one where a row or column contains minimum unit cost. If there is again a tie, select one where maximum allocations can be made. Going back to the problem, we can see that the difference 50 is left That means we will be allocating 50 over there. And this comes, that means we are left with, in column A, E, we are left with 175. So we will be allocating down the line over there. Now the thing is that how to proceed further. Again, here largest difference is 5 in the second column, as the minimum cost is in C12, that is 113. So we can allocate minimum of 50 to 225 over there, what we have done. Continue this till all availability of the remaining rows in column as shown above. On the right side, complete allocation has been done as per this method. Now, we have to calculate the transportation cost. This is the final solution in this case. Here, we have to multiply the same method we have to be followed, that is 200 by 11 plus 50 into 13 plus 175 into 18 plus 10 into 125 plus 10 into 275 and 10 into 125. We get the value at 12,075. Here we see that the transportation cost by NWC method is 12,200 and by web method it is 12,075. Now, how to proceed when the transportation problem is unbalanced? That means demand and supply values are not equal. The problem is we have a demand of 145 and we have the supply of 105. So in that case, we will be adding a row in which the unit values will be 0 and we will be adding a supply is 40. So here we can see we have added a row, fourth row, which has a unit value of 0 and the assigned supply unit is 40. If the total demand is greater than the total supply, a dummy source, that is dummy row, with equal supply equal to demand surplus is added, what we have done. Now, the problem is similar to the earlier one. We will be applying Module's approximation method. Minimum value. The problem is like this, and the solution, optimal solution is obtained. Here, the same method has to be followed. And we see that 1 into 10 plus 6 into 60 plus 4 into 10 plus 6 into 10, 3 into 50 plus 0 into 40. Here we get the transportation cost as 550. If the total here, if the total supply is greater than the total demand, then a dummy column is added with the demand equal to supply, surplus is added. So here in this problem, supply is greater than the demand. So we are going to add a column over there, which is dummy column D. Unit values are 0 and a demand value of 5 is added to it. That means now this has been converted into a balanced transportation problem. Proceeding further, with that case, we are going to get 9 into 20 plus 13 into 35 plus 0 into 5 plus 11 into 10 plus 5 into 50 plus 4 into 40 and 7 into 20. We get a value of 1295. Now, how to maximization of transportation problem? In this type of problem, the objective is to maximize the total profit or return. In this case, convert the maximization problem into a minimization problem by subtracting all the unit cost from the highest unit cost given in the table, and we have to solve it as find the optimum policy schedule and the profit associated with it. This is the problem which is given to us. We can see that the demand is 210 and the supply is 230. It's not balanced one. What we are going to do, and we have to maximize it. This was the problem given to us. Now we have to convert this table into a minimization table. Conversion to relative loss table by subtracting the largest element. Here in this table, the largest element is 95. So we will be subtracting 90, all these values, all the values from the table. So we get the right one matrix, what we can see 0, 15, 25, 35, 20, 30, 35, 45, 25, 50. This is the condition, and now we have a supply of 230 and demand of 210. If the total supply is greater than the total demand, a dummy destination dummy column has to be added with the supply surplus. How this will be? This will be transformed like this now. A dummy column has been added. The difference of the value is added to it. And now we will be following one method or northwest corner. Normally, we apply northwest corner rule. The north minimum allocation, we will start from the left corner of the table. And we will be reducing it. That means we will be eliminating its demand and supply in each row and column. So we are going to get a solution of 0 into 40 plus 15 into 30 plus 30 into 20 plus 30 into 20 plus 45 into 40 plus 55 into 50 plus 65 into 10 and plus don't forget that 0 plus 20 to write 0 into 20. We are going to get a transportation cost of 13,000. Then comes your modified distribution method, which is known as Modi method. Modified distribution method is also known as Modi method or UV method because we will be using UV over there for solving the problem, which provides a minimum cost solution, that is the optimum solution to the transportation problem. The following are the steps which are to be followed in this method. Number one, find out the basic feasible solution of the transportation problem using any one of the three methods discussed just right now. Second step, introduce dual variables corresponding to the row constraints and the column constraints. If there are m origins and n destinations, then there will be m plus n dual variables. The dual variable corresponding to the row constraints are represented by ui, where I is equal to 1, 2 till m, whereas the dual variables corresponding to the column constraints are represented by v, j. That means j will be taking the value of 1, 2 till n. The values of dual variables are calculated from the equation given below. In that, ui plus vj will be equal to cij. We will be going through the problem, then we will be in a position to understand about all these terms what we are discussing right now. Any basic feasible solution has m plus n minus 1. Thus, there will be m plus n minus 1 equations to determine m plus n dual variables. One of the dual variables can be chosen arbitrarily. It is also to be noted that as the primal constraints are equations, the dual variables are unrestricted in sign. If xij is equal to 0, the dual variables calculated in step 3 are compared with the cij values of this allocation as cij minus ui minus vj. If all cij minus ui minus vj are greater than equal to 0, then by the theorem of complementary slackness, it can be shown that the corresponding solution of the transportation problem is optimal. If one or more ci minus ui minus vj is less than 0, we select the cell with the least value and allocate as much as possible subject to the row and column constraints. The allocation of the number of adjacent cells are adjusted so that a basic variable becomes non-basic. Step 5 is a fresh set of 12 variables are calculated and repeated. The entire procedure from step 1 to 5. Now we consider a transportation problem. Here we have demand and supply on the values are given to us. How we will proceed? We will be using any method what we have discussed to find the initial basic feasible cost. So the basic feasible solution using the least cost method is x1 150, x2 260, x2 540, x3 150, x3 210, x3 350, and x3 440. This is the basic feasible solution. Now, the 12 variables UI, U2, U3, VI, there are 5, can be calculated from the corresponding Cij values. That is U1 plus V1 equal to 1, U2 plus V2 equal to 12, U2 plus V5 that is 1, U3 plus V1 equal to 14, U3 plus U2 equal to 33, U3 plus V3 equal to 1, U3 plus V4 equal to 23. Now, we choose one of the 12 variables arbitrarily as 0, that is U3 equal to 0. As it occurs often in the above equation, the values of the variables calculated are now U1 equal to minus 13, U2 minus 21, U3 0, V1 14, V2 33, V3 1, V4. We have calculated all the values of U and V. Now we calculate Ci minus Cj, Cij minus Ui minus Vj for all the cells. That is, and where Xij is equal to 0, that is unallocated cells by the basic feasible solution. Cell 1, 2, cell 1, 3, 1, 4, 1, 5, all these values are calculated. So we get minus 11, 25, 26, 42, 31, 36, 80, and 4. You can see that over here, there is one value which is negative, that is minus 11. Note that what we will do in the next iteration, that is x12, will be basic variable changing one of the present basic variables non-basic. We also observe that for allocating one unit cell, that is cell number 1, 2, we have to reduce 1 unit in cell 3, 2 and 1, 1 and increase 1 unit in cell 3, 1. That comes the net transportation cost for each unit of such reallocation is minus 33 minus 1 plus 9 plus 14, which comes out to be minus 11. The maximum that can be allocated to cell 1, 2 is 10. Otherwise, the allocation in the cell 3, 2 will be negative. That means the revised basic solution will be x1 140, x12 10, x22 60, x25 40, x31 60, x33 50, and x34 as 40. Now, we move to another problem which we have to determine the optimum distribution of the company in order to minimize the transportation cost by Vogel's approximation method. The problem, the company has 3 plants, A, B, and C, which supply warehouse located at D1, D2, D3, and D4. Daily plant capacity are 11, 13, 19 respectively, and their daily warehouse requirements are 6, 6, 8, and 23. The unit transportation cost is given to us. We have to determine the optimum distribution for the company in order to minimize the transportation cost. With this, we will be concluding today's session and we will be continuing with this in our next session.